We are the students from the Guaymas Tlacomulco, and we are the number 14. The team which we talk about is LGBT Islam, and the team is made up for Ezequiel Eduardo Flores Yebra and me, Luis Ángel González Flores. As you can see, we're going to the index. The topics are Islam, what do Islam mean, what is Islam, map representation, the Islam problem, Islam application, particle filter, Islam application, LGBT Islam, what is deep image, what is LGBT, Islam with LGBT, example of LGBT Islam.
Alright, and it's very important to say that our main topic is LGBT Islam, but in order for us to get our complete knowledge, we're going to have to go back to the beginning. And we're going to start off by Islam and go little by little until we reach our main topic, that is LGBT Islam. Islam, we're going to see in the next slide. Basically, we're going to break this down in small pieces. Breaking first, what does the S mean? S means simultaneously. As you can see here in this image, simultaneously means doing two actions at the same time. As you can see in the image, the person is punching and kicking. Alright, then the L, what does the L mean? Localization. We're going to deduce our position or our location when a map is given to us. Basically, as you can see in the image, we are given a map, but we don't know where we are. That's the part we're going to have to deduce. That's what localization means in Islam. And they is an, basically a combination, and last but not least, mapping. We're going to deduce a map given our localization. For example, they give us this map you can see here in the image. We're going to have to deduce where our robot is and where it's facing, its positioning. And when you combine all of these different types, we're going to have our SLAM. It's simultaneously localization and mapping. That's basically, SLAM is the acronym and this is the meaning. Next slide. This topic, another team already explained it, but it's very necessary. So basically that's what SLAM means. Not its definition, but what each letter means, which is simultaneously, localization, and mapping. Alright, next slide.
The Islam consists of making a map of the place we don't know, and at the same time is keep track of the robot in the travel.
Like we were seeing in the past slide, basically we're going to have to do two actions at the same time. That's where simultaneously comes in. We're going to have to keep track of our robots. That's what the part of mapping is. And we're going to have to deduce what type of map it is, or map the entire area in case we don't have a map. That's what localization would come in.
We are three types of represent the map. The first is a grid map. Is a more precision of location, and they are easier to use when you want to know the robot latitude and longitude.
Basically, grids are mainly, in case some of you don't know what a grid map is or what a grid is, basically grids are used when we're trying to do some geometry, or we also use it in trigonometry, that we use them in when we want to form our maps, and form our, what's it called? Basically, it's for creating shapes and what's the name's slipping away, but basically we're using and geometry to these locations and find out their distance and their characteristics, each one.
And the 3D maps are the more used for illustrating. The 2D is a map is more used for painting areas or following roads and GPS.
So these are three types of maps that are going to be presenting in what we know as SLAM. When we're going to see the topic of RGBD SLAM, we're going to be using more 3D maps for the localization part, and for the mapping we're going to be using the 2D maps. The grid maps are only going to be used in case we want to learn its exact location or its trajectory and its position. Alright, and so we're going to be going into what we know as the SLAM problem. The SLAM problem has something similar to what we know as the chicken or egg problem. Basically, the chicken or egg problem is that what came first, or the chicken or the egg. Alright, I'm going to tell you guys the solution to this problem in case some of you guys don't know the actual solution. Basically, years ago, before what we know as the chicken existed, there were two different types of birds. These two different types of birds mated and they gave birth to what we know as a chicken. So for a chicken to hatch, it would need to come from an egg. So basically, after these two birds mated and formed what we know as an egg, and this egg was going to be originator to what we know as a chicken. So the solution to this problem is that the egg came first before the chicken. Alright, then what does that have to do with SLAM? Basically, SLAM, we have the problem that we need a map and we need the robot's location. But what do we do when we don't have either of those two? The solution that a lot of people that use SLAM are giving is that we either give the system this map or we give the system the robot's location. And having one of these two, we can use algorithms to generate and give us the other part. Next one. So basically, these problems are very similar, but they have a solution. We have to give it our own solution. Alright, then the SLAM problem. Basically, this is what I just said, that we need a map or we need the robot's location. If we don't have both of those, we cannot do anything because we wouldn't know where the robot is or what type of area its location. We need the map or we need its localization. As you can see here in this image, we're going to need at least one of those two. Alright, so what's another problem with SLAM? That a small error on the map or a small calculation on its location of the robot can generate consequences. As you can see here in this image, in this case, this robot right here is hit by the car because the robot didn't have the exact location on its map. Basically, in this image, the robot, the data that the robot was sending, it was saying that the robot was on the sidewalk. But in reality, it was on the road, and the consequence is the car just ran it over. It's very important to never, the word I'm looking for is, never trust in the data that the robot's sending when we're doing the first trials. It's important to always check the data and compare it with our actual map or its actual location to see if it's correctly is in the right location, or else it's going to be hit by a car, or it's going to crash, or it might hurt somebody, generating losses to the people that are managing the robot or the company. Alright, our next topic is the particle filter. Basically, the particle filter is going to help us establish the robot's position. As you can see here, this is a map of the area. Going back to what I was saying in the last two slides, we're going to have to give the system or either a map or the robot's location. In this case, we're giving the system a map of the area. As you can see here, we don't have any idea where the robot's localization is, where the robot is located. We don't see any dots or any types of symbols that represent the robot's location. Basically, to represent the robot, we're gonna have to form a red dot. That's gonna symbolize the robot's location. Next slide. As you can see here, the particle filter is gonna start exhibiting particles all over the map, and it's gonna be in 3 different processes, as you can see in these 3 images. First, the particles are gonna zone over the map until they hit or detect the robot in a grand ratio, as you can see here. As we don't know exactly the robot's location, but we get an idea. Then we resample the area. As you can see here, we have these red dots. They represent possible locations for the robot. And lastly but not least, we update our map, giving us possible locations where the robot might be. We're going to have to redo this process, not once, not twice, but a lot of times, in order to get the exact location. Next slide. As you can see here, each time we let the particles go, the red dot is forming and giving us a better exact location of the robot. As you can see here, we let these blue particles represent the particle filter. We let them out, and the data that we get back is a possible location of the robot. As you can see here, the point is basically getting smaller or giving us an exact location. It doesn't have, can you go back a slide? It basically isn't all over the map. It's an exact location. Go back. Yeah. Right. Until we get what we know as a red dot indicating the robot's exact location. Right. So we're going to be doing this a lot of times. Following these 3 steps, we let the particles on the map that represents blue. Then these particles are going to give us a possible location of the robot. We're going to continue doing this until we get an exact location of where the robot is or where it's going. Next slide. Alright, go back. Basically, but we have to remember that meanwhile we're trying to locate the robot, at the same time the robot is moving. That's why, go back. That's why in this image, it's telling us that the robot can be in this area. But at the same time, the robot is always in movement. So the particle filters. Next slide. Right. And in this image right here, you can see that the robot moved. The robot is always going to be moving and it's never going to stop. The particle filter, in between each update, the robot's not going to be in the same position. It's going to move. So it's very necessary we keep on doing this until basically we won't need to liberate any particles, and we're going to have the exact location. I think that's all. Yeah, that's all.
In indoors, SLAM is an automatic vacuum cleaner, lawnmower. In air, the SLAMs are used in surveillance drones. The underwater is used on mapping and reef monitoring. In the space, the SLAM is mapping of shorelines using unmanned vehicles and space human can easily to get to. The underworld is the use of exploring of mine, caves, or mapping of them.
Basically, SLAM is basically the mapping of an unknown area, as we already defined that in past slides. Another thing that changes in each application is the area in which we're going to be applying SLAM. Or is it going to be air? Is it going to be underwater? Is it going to be underground? Or even in space? It's not going to change. The method's not going to really change. We're just going to have to do some modifications depending on which type of area or terrain we're going to be liberating, or our drone, or our robots, or types of sensors. Basically, mobile robots. Alright, then we're going to be entering the RGBD SLAM territory. just like we did in the slam, we're going to break this down into smaller topics. You guys are probably going to be asking yourself, what does the def image have to do with RGB slam? It's not even mapping, but it's an important key factor in order for us to do the RGBD slam. Right then, first, what is the def image? As you can see here, the def image is obtained using a system. In this image right here, we have a Microsoft Kinect that is used for Xbox. These Kinects are very good cameras and offer us the possibility to take good RGB images and depth image. Basically, depth image, as you can see here, it's basically the distance between an object that's in the image and the plane. This here is the original image. It's an RGB. This is an RGB image. Alright, you can see here is the differences. The only difference is that here we're taking this computer screen, and it's gonna show us basically the distance between this computer image and the background. In this case, it's a table, and it's gonna basically eliminate any extra objects. As you can see here, that we have these utensils, and in the depth image it doesn't have anything. So basically, the depth image is the distance between the image plane and the background plane. Or if you want to see it in another way, it's basically the difference between the RGB image and the background plane.
What is the RGBD? RGBD is a combination of the RGBD of an image and this deep image.
Basically, here we have the depth image and our RGB image. To do an RGB slam, it's, as its name said, if you look at it, we have the first part, that's the RGB, and the depth image. In order for it to do its main objective, is combine the two, and boom, we have the RGBD slam. Alright then, what is RGBD? As we said before, it's a combination of both images, the normal RGB image and the depth image. As you can see here, we have an ordinary RGB image, we have the depth image, we combine it, and boom, we have this image that is an RGBD image. As you can see here, we have another example. We have our two RGB images. We have its depth images. And when we combine them, it gives us the RGBD image. And basically, if we want to look at it in a 3D perspective, the image that it's going to generate looks something like this. Alright then. Now this is the main part of our topic. The slam with RGBD. It has 3 steps. The first step is basically taking the image. As it sounds stupid, but basically it is. We have to take the image, we have to take a depth image, and we have to combine the two so it can generate what we have here, our complete RGBD image that we're going to be working with. Next image, next image, next slide. Alright then. Now the second step. The second step, as you can see here in this image, it's going to be, which one is it? It's right here. We have our normal RGB image and we have our depth image. We combine them, and in this step, after we get the RGBD image, we're going to be extracting or basically taking points of interest from each part of the image that might interest us. As you can see here, all these lines represent points of interest that are important to us or are going to be interesting us for the later step. As you can see here, we have all these connections that represent points of interest, like I just said here before. Alright then, after this, it's going to pass through a constraint that ensures each matching pair or feature points correspond to a 3D point in each frame. Basically, this is like a filter that's going to basically ensure that each of these points correspond to a 3D point in a past frame. I'm going to explain it a little bit in depth in the next slide. And lastly, the map building. Alright, what was I saying in the past slide about these points of interest? Basically, we're going to be comparing, for example, we have this part of the image. We don't have the complete image yet. So we're going to be taking some points of interest. When we take the second frame, we're going to compare these points of image from the new frame to the past frame in order for us to get a full image. And basically, can you go back a slide? What are 2 slides? Another one. Back. Back. Front. Back. We're going to use this example. Basically, we're going to try to form a map using these points of interest that I was talking about. Now you can go back now to where we were. And we're going to be doing this for each type of frame or each image that the robot or that basically the robot's going to be taking these images in order for us to construct a 3D map, as you can see here, using the RGBD SLAM. It's basically the same thing as SLAM, but the only difference is that it's taking images, combining an RGB and a depth image, and forming a complete 3D map. That's basically the only thing that's different between this and the SLAM. It's mapping, but it's using 3D and RGBD and depth image, a combination of 2, and points of interest that from each frame I want to say the word saving. Basically, it's not saving, but it can apply. Saving in each image we are taking. So later, the computer can process our new 3D map. And where is the SLAM in this, or what does the SLAM do in this? Basically, as you can see here, in this grid, the red line is the true line. It's basically the route that the robot's going to have to take in order for it to get out. Now the blue line is the one we're going to be estimating, taking into account all these viewpoints, all these points of interest, and the mapping that the robot is doing. And it's generating our 3D map using the RGB. And once we have our map, the robot is going to estimate, with help of the RGB, this image, where it can go, or what it can, or basically what path it can follow without obstructing or crashing. That's what RGBD SLAM is, basically. It's basically an estimate of a route that the robot can go through using RGBD and with the combination of a depth image, so that it can navigate through a labyrinth or a place without crashing or suffering any accidents. This is the example I already explained of how the RGBD SLAM works. Basically, we have a camera, it takes an RGB image, it takes a depth image, it combines both of them, and we have our RGBD image. This image goes through processes. In the processing, like I said before, we take points of interest that can be either walls, and we combine them to our past images that the robot is taking, so we can get and form a 3D map. As you can see here, the process is repeated until we have a complete map of a 3D map of the area. Once we have a 3D map of the area, we're gonna put in SLAM, like I was saying in the past slide, where we're gonna be. Can you go back a slide? So we're gonna be forming a route that the robot's gonna follow, so that it won't crash or suffer any accidents. That's where SLAM comes in. With the help of our 3D map, the robot's gonna estimate, or the system, depending if you have both of them in the same place or it's separated, it's going to estimate or deduce where can the robot go and give it its path. And lastly, we're going to generate our trajectory map, or a map that the robot's going to follow in order for it to get out of the labyrinth or out of the place. And that's basically, these are some references, that's basically what RGBD SLAM is. Just to give a small, version, RGBD SLAM is basically mapping using a 3D map that is generated from RGB and a combination of depth images that is then processed with points of interest so that we can generate our 3D map. And with the 3D map, we are going to generate a route that the robot can follow through without crashing or generating some kind of accident. And lastly, we're gonna have a video that's gonna show you guys how the robot puts this in action. That's gonna be integrated in the presentation that's gonna be sent. Alright, and thank you for your attention. That's all.